information leak by stack reading using the blind ROP attacks. And let me briefly go over the ideas of how the information leaks here. First, attacker injects a payload for information leak into the target. Then the code pointer in the target leaks to the attacker. Then attacker crafts new exploits using the leaked code pointers. Then a crafted exploit is injected into the target again, and because of the exploits, target memory leaks attacks. And the attacker analyzes the contents to build an ROP chain and launches the next stage of the attack. That's the scenario. But when Zeus compiled a program response, they encrypted the return address. The attacker may inject the payload, and the encrypted return address may be disclosed. But they craft new payloads and send back to the target. But the target has changed the encryption state. So the leaked information overlays at this point. So they cannot succeed in the data attack here. So information leak, by using the Nginx server, I'm going to show two videos. One is a successful attack and the other is a failed attack. This is the target, and below there is an attack side here. And we inspected the target. There's Nginx master server, master process, and also a worker process. And this is the script for the blind ROPs. And it's so fast it goes. Anyway, it first investigated the length of the buffer. So after finding the buffer size, then begin to override beyond the buffer area. So they read 1 byte at a time, the target. And they prepared the payload and they sent to the target in this. So that's the script, actual text here. Then you should notice that how the worker process changes. The process ID is changing. Can you read it? That's they are reading a byte. This is the confirmation of the length of the buffer. They try reading, and it is worker process and dies and relaunched again and again, so it's changing continuously. So it's a characteristic of a resilient programs. Attack kills them, but they revives. So attacker can read out as much as they want. So in memory there are zeros, so they just leak the zeros, but eventually they got the 8 bytes and this method, 7FF, something like that. So that's incremental byte reading against the resilient program by using blind ROP attacks. So, but the Zeus compiled program. So let's see how Zeus can defend against that attack previously launched. So it's the configuration is same. Web server, that's the process and local process. And the attack script is the same, but start the attack here. And it tries to read incrementally byte by byte. And after confirming that the length, they can confirm the length because the process dies. So when they notice that when the process dies, then they know how much byte they injected. They can see that the length of the buffer. And they begin to probe that beyond the buffer. This one, they try really hard, but they can never read out any byte from the process. You notice that there's so many local processes killed and relaunched again and again, but they never leak any byte. That's the power of dynamic re-encryption. Well, without dynamic re-encryption, attacker may disclose the encrypted return addresses or whatever the value inside the memory. And even encrypted and disclosed pointer values may be analyzed. Because in encryption-based approach, people are relying on some really efficient operation, like such as an exclusive OR for the encryption and decryption, and it's really easy to break. So anyway, the re-encryption does not allow any leakage here. Anyway, it's done. Anyway, there's been so many walk-up processes, but no walk-up process leaked any return addresses. Okay, this is the first demo. And another one is return-oriented programming. Well, Robert already explained about what is the return-oriented programming, but let me briefly go over it. Return-oriented programming is a code reuse attack, what called an arc injection attacks. So connecting the control flow among the already existing instructions. Exploit is a chain of gadgets, addresses that should be loaded into the stack buffer and some data. That's an exploit. And the gadget is a sequence of instruction ending with the return instruction. And the set of gadget is just string complete programming language, a lot of mentioning. So if any attack load this exploits in the stack buffer area, then we can move from one gadget to another gadget by using the return instruction. Return instruction refers to the return address in the stack, and then this return address refers to another gadget then this return instruction, then refers to another gadget. This kind of connection is achieved some what is called the Turing complete programming language speed. So now I'm going to show a shell code launching a shell by return-oriented programming, and also that another video that can be prevented by the Zeus compiled program. The scenario is like that: an attacker injects an exploit into the target's buffer in stack, and the exploit is made of a shell code and the RP chain, and a return address is overwritten to the starting address of the RP chain, and the RP chain converts the page of injected shell code to an executable one. That's the mission of the RP chain. Then shell code runs and opens in a socket, listening to the attacker. Then the attacker establishes a TCP connection using the netcat. Then the attacker can interact with the target. I show that the attacks video. And actually, this was happened in the Nginx Web Server in 2013. Let me show these videos. This is a vulnerable version. So as before, this is a target side, and the lower window is attack side. Also, there is a master process and a worker process. Just to see that how the attack works here. It's a script. And this is a shellcode part, and this is it's a gadgets, RP chains here. So this one will launch the socket connection, and this one will convert the shellcode and executable pages. And attack payloads will be sent through the HTTP protocols. Actually sending the protocol here. Using the protocol sends here. So let's start that attack. Executing the shell script. This script is for the demonstration, and the actual attack is done by this Python script. This message is for your guide, but we cannot read it, but don't mind. You may notice that some, yes, attack succeeds and the netcat is executed. Then attacker sends that all the comments that the Linux or Unix can accommodate, like PWD, and it shows and where that the control is, and the directory listings. And sometimes we can display the password file here. So if password file is disclosed, then we may know that who the users are. So that's the attack. But the dynamic re-encryption, okay, this one. Same setup, so target, and it's on the attack side, same configuration. Anyway, it says end of failure. exploits. Well, when the attack side tried to netcat connection, the failure message is sent back. That's what we extracted from the failed image. They cannot succeed in because of dynamic encryptions. Well, this is the end of my presentation. So I'm not sure how much you get what I'm talking about. This is real bad. Okay, good. Yeah. So let me briefly summarize what I mentioned regarding the. I didn't prepare any conclusion slide, but let me go briefly over the status of Zeus implementations. What we have done is encrypting all the code pointers, return addresses, function pointers, in particular the function pointers user-defined, and the function pointers for the shared library, and the function pointers and compiler-generated. All function pointers are encrypted. Among the encrypted function pointers, currently the return address is dynamically re-encrypted. Whenever program control flows into some vulnerable regions, then they update all the encryption state. So basically, Zeus compiled program protects themselves by encryption, but with just the static encryption, they are vulnerable to the information leak attacks. But Zeus guards or protects the Zeus compiled program by promoting the statically encrypted code pointers to dynamically encrypted code pointers. So while attackers may try to override a code pointer, but they cannot succeed because they cannot hit the moving target correctly. Even though that the encryption state is static, it's really hard to hit the encrypted address. If the address bit is 64 or 48-bit or whatever, anyway. Even 32 bits, it's really hard to correctly guess at one time. But even the dynamic re-encryption makes it harder and harder. So information leak is mitigated quite a bit using the dynamic re-encryption. So as a conclusion, I'd like to say ROP or blind ROP, all those attacks require some information leak attack. So without blocking the information leak, then any further subsequent mitigation strategies becomes somewhat diminished in its effect. So anyhow, that information disclosure or information leak should be blocked. That's why we try to make a re-encryption technique. So this one is fine. We designed this one and will be implemented it. And a programmer defined and compiler generated, it will be a really hard problems. And in my personal opinion, it's almost impossible because of the typecasting and pointer aliasing problems. They may be, these two pointers may be encrypted statically, but dynamic encryption will be almost impossible. If programmers want to preserve the correctness of the program, then they cannot dynamically re-encrypt that one. But the static encryption is to some extent is possible. But even in that case, we may have to sacrifice some compatibility but so far we confirmed that it's compatible up to the point, let me say, compiling the standard C library in the server programs. It's not 100% compatible, but practically has no problem in protecting program based on the encryption. But one thing, in our analysis of a stack benchmark, we noticed that there will be more than 85% or between 80 and 85% are return addresses. So that means dynamic re-encryption protects majority of the code pointers, and return addresses are always the favorite from the outside attackers. So I think it's a practical values of protecting programs.
Well, so these are the dynamic